Okay. Okay, welcome everybody. I think you can. I mean, can you hear me? So, would you say yes? Okay, thank you very much. Okay, so welcome back, and this is the second week lecture of the Introduction to Logic in Computer Science. So we will continue to discuss some basics of propositional logic today, and we finish off this slide set and then move on to equational reasoning. Okay, so last week we talked about the syntax and semantics of propositional logic, and then I said the basic intuition about propositional logic is it's very much like a Boolean expressions in programming languages, except that the only variable we talk about are Boolean variables. And the focus of propositional logic is, in a sense, focus is on the logical connectives of the Boolean expressions like and, or, and negation, and so on. So, and then to study propositional, we're gonna study computational properties of propositional logic. And to do so, we need to clarify, we need to formalize what we mean by the propositional logic more precisely. So we have to say what syntax of propositional logic is and what is the semantics. So that's what we did last time. So we said the syntax of the propositional logic is something defined inductively, as you see in the slide. We have a collect countable infinite set of propositional variables, and the terms, well, formulas of propositional logic are constructed inductively as what you see on the screen, either true or false, propositional variables, or we can construct a new formula out of existing one using negation and then or. And other logical connective that you see before, like implication and equivalence, can be constructed from what we have here. And one important property of this propositional logic is that because everything is defined inductively, we can, if we want to define something on the propositional logic formula, we can use structural induction. So we set the structural induction. See, yeah. So the idea of structural induction is essentially write a recursive function on the propositional logic formula. And then the recursive function, it has to deal with the base cases. Base cases are true, false, and propositional variable. And inductive cases are negation, conjunction, and disjunction. And we define the size, but the more important example that we covered last time is the semantic functions that we discussed last lecture. And then the semantics functions of propositional logic formula is a mechanism to assign 0 and 1 to each propositional logic formula. And then it's parameterized by so-called assignments. That assignment provide a meaning to all the propositional logic variables. So it's, let me use this draw. So it's parameterized by assignments, and that assigns the meaning to all the propositional logic variables. And then this semantics extend how we can use this assignment to give a meaning to any propositional logic formula. And then the way it's defined is exactly what you expect. For true, false, it becomes 0 and 1. Propositional variables, this is the place where we use this parameter assignment A. And the other cases are exactly what you already know before. negation means essentially negation, conjunction means conjunction, disjunction means disjunction. But the point I bring this up is because this is a formal way to define what each propositional logic formula means. And this formal understanding will help us to talk about something more interesting. I don't know. Okay. Right. And so important concept we covered after discussing semantics was the so-called satisfiability and validity and satisfaction relation. And these relations really say when the assignment, which gives a value to all propositional variables to zero, I mean, the assign 0 and 1 to propositional logic variables. So it assigns 0 and 1 to variables. And with these satisfaction relations, this is written here, and then satisfiability and validity, they talk about the relationship between assignment and formula. Satisfaction relation that you see here, I mean, it describes the relationship directly. It says that the assignment A, sometimes it's also called a model. A satisfies formula F if formula F evaluate to 1 under A, according to the semantics that I showed you in the previous slide. The satisfiability means it has at least one satisfying model. And then validity means the formula is always true. Formula is true for all the models. So that's what the last part say. And last time we said so one of the important computational questions involving the satisfiability and validity is the so-called satisfiability problem, which says that given a formula F, this problem asks us to to check whether the formula have a satisfying assignment or not. And then there are many, this is one of the best known so-called NP-complete problem, okay? And so which means, I'm gonna tell you what it is. I hope you already heard about it before in the algorithm course. I'm gonna remind you what it is later. But it means that it's more difficult than the usual algorithm that you encounter in the algorithm course. But although this problem is considered quite difficult, and there are many existing solvers, satisfiability solvers. So this Boolean satisfiability problem is, it's a kind of examples which in theory it's very difficult, but in practice there are many efficient solvers for this satisfiability problem. So what we did at the end of the last lecture was to encode some of the well-known problems using to the satisfiability question. Erase this. So we were in the middle of encoding Sudoku problem. And the Sudoku, has a 9 by 9 matrix, which contains valid numbers between 0 and 1 to 9, including 1 and 9. And then question asks us to fill in. It has some of the boxes in the matrix have numbers, but some other boxes does not have a number. And then this question asks us to fill in these blanks in this matrix, such a way that all the rows have all the numbers between 1 up to 9. All the columns have all the numbers between 1 up to 9, and also all the 3 by 3 squares, like maybe highlight, and like this 3 by square here. After filling in the blank, this 3 by 3 square should have all the numbers from 1 to 9. So that's what we have to do. So the Sudoku problem is given this configuration, figure out which number should go into each blank. And we are thinking about solving this problem. So we are thinking about solving this problem using by encoding it into a satisfiability and invoking satisfiability solver. So, and then the key step to solve this problem, as well as one other problem that we discussed, which is called Hamiltonian Path problem. In both cases, the key step is to come up with how to use propositional variables. So this is often like many of the problems in real world. If you want to use satisfiability solver to solve the real world problems, the key step you have to do is to encode some fact about the real world using propositional variables. So in this case, what we're gonna do is we will introduce 9 times 9 times 9 propositional variables, which are called, I think maybe just using this is better, which are written here. It's xijk. And then this is a propositional variable, so it has gonna have a value either 0 and 1, but it will have a clear meaning. And then that meaning is if xijk is true, if and only if the grid position ij contains the number k. Okay, so this xijk really say the ij position in the board will contain the number k. So that's what this Boolean variable is encoding. So then the problem of the step of encoding this problem into satisfiability boils down to expressing all the rules of the game, or the Sudoku game, in terms of this, express all these rules in terms of these propositional variable xijk. So we're gonna encode 3 rules, and then in terms of using the 3 rules that express this Sudoku problem. The first rule said each number, in each row, every number should, in each row, every number should appear. In each column, every number should appear. The second rule, second property we want to capture using logical formula is that each 3 by 3 blocks should contain every number from 1 to 9. Okay, and then the last part we want to say is each square should not contain two 1 numbers. So these are the 3 properties we want to encode. And because we have an understanding about what xijk means, which means that ij position contain number k, we can, by using xijk, we can express these 3 properties. So I'll show you the first property. And the first property is written this way. Okay, because this is iterated conjunctions. You see that iterated conjunction over I, iterated conjunction for j, and there's iterated disjunction for I and k, iterated disjunction for j, and the formula involve xijk, and those have something similar. But a better way to read what this formula actually means is that for every I, conjunction is essentially correspond to universal quantification in this case. For every I, which means for every row, and for every number k from 1 to 9, we should be able to find a column j such that the ij kind of entry should contain number k. Okay, so for every row, every number from 1 to 9, there exists a column where this ij box contains number k. So let's express every row should contain all the numbers from 1 to 9. This one is very, very similar, and it expresses the properties about the columns. So say for every column j, every number k from 1 to 9, there exists row I, so that this xijk is true. So every column, every number, there is some entry in that column, or some row in that column, which contain number k. So that's what this F2 is saying. Okay, so now I will give you maybe 5 minutes so that you can express the other 2 properties using, this xijk. Okay, so I'll give you maybe until 9:18, so solve these for the problem. But just imagine that you didn't see these 2 answers and try to solve these 2 questions. By the way, while solving it, if you have any questions, you can raise your hand, or you can ask me in the chat box. So, okay, so let me show you the answer here. So then for the second property, actually the description is pretty similar to what we did for F1 and F2. We say that for every U and V, which means every 3 by 3 block. So these guys are talking about every 3 by 3 block, and every number K from 1 to 9, we can find some entry in the 3 by 3 block. So that's what this disjunction is saying, such that that entry will contain the number K. So that's exactly this is the second property. And then the last property said for every row, every column, which means every entry in this 9 by 9 matrix, the 9 by 9 grid, if we pick, I mean, it's never the case that this entry will contain two different number K and K prime. So this last part say any K and K prime which are different, it will never the case that this Xijk is true at the same time Xijk prime is true, which means, I mean, if both of them are true means Ij contains both K and K prime. And then the last one said the no square contains two different numbers. And it turns out if you do so, then actually that's a complete description of the Sudoku. Oh, actually you have to do one more. One more thing is in the specification of the Sudoku, it has some pre-existing numbers. For instance, this matrix, the entry at 1, 2, row I, column J will contain number 2. And we have to express this type of kind of existing numbers using some other logical formula. So that for F5 express the initial configuration. So in this case, because the 1, 2 contain number 2, we said X 1, 2, 2 should be true. And then similar way, we said because the the second row and the first column will contain number 8s. We use this x2, 1, 8 has to be true as well. Okay? Because I mean, that's this x2, 1, 8 exactly expresses the 2, 1 entry contains number 8. So that's a descriptions about the initial configuration. It turns out if we combine all of F1 up to F5, which we defined in this slide and the previous slide, that provide a complete description about this particular Sudoku problem. So for instance, I mean, one other properties of the Sudoku is the fact that you see in F6, which say, I mean, every row will never contain two, right. So for every row and for any numbers, no two columns of that row will contain the particular number k. So for every row I, every number k, we can't really find two different columns j and j prime, both of them contains k. Okay, so that's another property of the Sudoku. But this is the kind of property that's implied by F1 up to F5. So from the perspective of encoding this Sudoku problem into satisfiability problem, then just writing F1 up to F5 is enough. But if you view this encoding problem from computational perspective, something interesting happens, which is that although this F6 is redundant, sometimes adding something like F6 can help the performance of this satisfiability solver. So F6 is a redundant fact, but the solver for satisfiability problem can get some benefit by, from the existence of this formula like F6. So the point I'm making here is that the encoding from the existing problem to satisfiability question is sometimes an art. It requires some understanding about which encodings, which redundancy can actually help and which redundancy can actually hurt the performance of the set solver. But anyhow, if you just encode from the right F1 up to F5 without F6, and then they ask the set solver, and actually it can solve this Sudoku problem, okay? And this Sudoku is not very easy problem. I mean, it has, if you think about the number of variables, it has the 729 variables. And then if you think about how many, the kind of size of the truth table, it's really, really huge, okay? So simple-minded search is not going to solve this satisfiability problem generated from the encoding of the Sudoku. But modern set solver is pretty smart, and it uses very clever heuristics and algorithms. And because of this, it works. So some of my friends even told me that search solver can be understood as a generic search engine. So if you have some search problem, which is, if it has a search problem which has a polynomial time solution, that's great, you have to use it. But if you have a search problem which doesn't have a polynomial time, maybe because it's NP hard or maybe NP complete, then the kind of approach you need to think about is you need to think about how to encode that problem into set solver. That's because set solver is, in a sense, it incorporates, it contains many of the heuristics that people developed in the past maybe 20 or 30 years for solving hard search problems. Okay. So he said set solver should be understood as in a sense, one of the best generic search engines, which people have to think about to use whenever they encounter hard search problems. By the way, if you change, this is a side remark that you can ignore this, but if you change the problem from this finding a solution of Sudoku to counting how many solutions each Sudoku puzzle have, so the first problem is a lot easier than this counting problem, counting how many solutions each Sudoku puzzle have. And that becomes substantially more difficult problem. So that's that correspond to some complexity class, which is more difficult than NP complete. Here's another puzzle that we want to solve, which is a Hamiltonian path problem. Hamiltonian path is a path over a graph which visit every vertex or every node exactly once. And then actually what you see on the figure that appears in this slide is not a Hamiltonian path, it's called Hamiltonian cycle. But the idea is essentially the same. You want to come up with some path which goes along the edges of the graph that visits all the vertices in this path. Hamiltonian path may not exist, and we are interested in finding, we want to know whether a given graph has a Hamiltonian path or not. And if it's the case, we want to find an answer about this. Okay. And this can also be done by using satisfiability solver. So that's what we're gonna do. And just like before, the key part of this encoding, to kind of solve this Hamiltonian path problem using set solving is to, come up with a set of Boolean propositional variables and attach appropriate understanding or appropriate interpretations of these Boolean variables. So express essentially this problem in terms of Boolean variables. So here's a key step of this encoding. So to encode this, we're gonna introduce two sets of Boolean variables, xij and then eij. So eij is much easier to understand. Eij is true. So I and j, so we're gonna assume that the graph we are given has n vertices. So the graph has a vertices which are named 1 up to n. Okay, so vertices 1 up to n, and then so eij is where the index ij are over vertices. And then eij is true precisely when there is an edge from vertex I to vertex j. Okay. And then this xij is assuming that xij expressed the property that you see on the screen. It assumes there exists a Hamiltonian path. And then if there is a Hamiltonian path, then that path will visit every vertex precisely once. So this xij is true if vertex I is visited at the jth times. So vertex I in the Hamiltonian path is visited at the jth time. So then this xij is going to be true. Okay. So we want to set up a constraint so that if there exists a Hamiltonian path, then we can set this xij and eij in the correct way. If there isn't, then we can't really do this. So here's how we do it. And then we write some propositional logic formula that's a conjunction of some other formulas. And each of the formula will express the three properties that you see here. The first property is we want to say each vertex is visited precisely once in this Hamiltonian path. So that's this is how we write this. We say that for every I, the F1 said for every vertex I, there exists the J, which means that there exists a time when we visit this vertex I, okay, in the Hamiltonian path. So for every vertex I, there exists J such that we visit this vertex I at jth times in the Hamiltonian path. So this kind of meets the first criteria, which is this Hamiltonian path should visit every vertex in a given graph. The second one said, second one talk about, but we can't really visit, visit the vertex twice. Okay, so this one said for every vertex I, if j and k are different, then it shouldn't be the case that xij and xik are both of them are true. But in words, what this means is for every vertex, we will never visit that vertex twice in the Hamiltonian path. So that's what this second property is saying. Now there are two other properties we have to express. The second property is the path should go along the edges. So the last property is that eij encodes this set of edges correctly. So I will give you maybe 3 minutes to solve these two problems. So if you by any chance have no idea what to do, try to solve the third one, this last property. That's a lot easier than the second property. It's okay, I will give you the answer. And let's look at the last one. It says that this EIJ encode the set of edges correctly. And then formula F4 expresses this. So every IJ, which are connected by the edge set, EIJ should be true. And for every IJ, sorry, which are not, connected by the edge, the EIJ should be false. And then the F3 talk about, it says the following. Yeah, sorry guys. So you talk about the following. It says, for every vertex I, every vertex j, if there is a time in the Hamiltonian path when we visit I at the kth point, kth time, and then j at k plus 1th time. So that means we go from I to j in the Hamiltonian path. Then there should be an edge from I to j. Okay, so this path always go along the edges. It never go outside of the edges. So for every vertex I, vertex j, there exists a position in the Hamiltonian path where we visit I at the kth point, kth time, and then j at the k plus 1th time. Then there has to be there should be an edge from I to j. So that's how we express this F3. And once you express all these, then we can call a set solver, and then set solver will either say yes or no to answer the existence of a Hamiltonian path. And often if the answer is yes, so then the set solver will also return the appropriate values for xij and eij, which we can use to kind of construct Hamiltonian path for the given problem. So the point I'm making is that many problems can be encoded into the set solver, but to this encoding to the set problem in propositional logic, and can be solved by the existing set solver, such as G3 or some other things. But the key step in this encoding is to figure out how to use propositional variables to correctly express key properties of the original problem. And then for this set problem, so let's think about the algorithmic aspect of the set problem. And now if I ask you to solve set problem and then ask you to do it maybe in an hour, then there's a very simple way to do it, very inefficient way to do it, which is essentially construct a truth table. So given a propositional logic formula, look at which kind of propositional variables appears in the formula. If it is P1 up to Pn, you just construct a truth table which assigns 0 and 1 to all the propositional variables. You consider all the possible truth assignments. And each case, you just evaluate propositional logic formula that you have. And if one of the evaluation leads to 1, that's it. We found that this is satisfiable. Otherwise, we say it's not satisfiable. Essentially, construct the truth table, check whether there is an entry which contains 1. So that's the first algorithm. But this is a very bad algorithm. It always takes exponential time. It's bad not because it's exponential time in the worst case. It's bad because it's always taking exponential time. And then, but it turns out whenever people try to improve this algorithm, it becomes super difficult. And then actually so far, so people couldn't come up with polynomial time algorithms. And then also they couldn't come up with some algorithm which is worse than polynomial, but better than exponential time algorithm. And in fact, if somebody come up with a polynomial time algorithm that shows that the P is equal to MP, and then they will get $1 million, $1 million because it's a solution for one of the kind of most well-known open problems. On the other hand, there are existing, the set solvers, which solve this set problem in the many instances that arise in practice in a very, very fast. So some of the set solver can deal with maybe hundreds of thousands propositional variables. And so which means that although in the worst case, this is a very hard problem, people came up with many sophisticated heuristics that can deal with many common cases very efficiently. So that's why the Sudoku puzzle, which is naive approach, won't be able to solve the Sudoku puzzle, but the set solver can that puzzle very efficiently, very quickly. And other things, other comments I want to make is that the satisfiability question for arbitrary propositional logic formula is hard. But if you restrict the set of propositional logic formula to, say, Horn clause, or 2CNF, or so-called XOR clause, then actually there are polynomial time algorithms for these restricted classes of formulas. And we're gonna study about these algorithms later. And then the last comment is when we kind of encode some problem into set, the encoding itself shouldn't take exponential time because then the initial encoding will take just too much time. Okay, so that's it for this set of lectures. So what we did in this lecture is to study syntax and semantics of propositional logic, and then also we saw kind of how to encode some interesting puzzles or interesting problems into propositional logic, the satisfiability questions of propositional logic formulas. Okay, maybe I will give you maybe 30 seconds. Do you have any questions about what we covered so far? Okay, I will regard silence as you don't have any specific questions. So let's move on to the next set, next topic. So next topic is equivalence and normal forms. And this is also in some sense quite easy, but I will make it a little bit more difficult in a few places. Well, a little bit unusual in a few places. And the equivalences, in some sense, you learn about it in high school when you learn about logic, but there are something that I want to say a bit more. So this is a reminder of what we've done. We covered the syntax and the semantics of propositional logic, and we talk about, but for this particular lecture, we're going to focus on one of the properties in propositional logic, which is a logical equivalence. Okay. So just give you a reminder about the logical equivalence. We said two propositional logic formulas are logically equivalent if they evaluate the same value under any assignment A. So this really corresponds to this logical equivalence that you know. And then, so what we're gonna do is that we'll think about I will give you a few, I mean, this lecture is essentially about Boolean algebra. And in particular, several rules in Boolean algebra, and then it's have some deeper understanding about how these rules interact. And then the last bit is how to use these rules to convert propositional logic formula into some normal form. So the last lecture I mentioned this notion of decision problem. So decision problem is an algorithmic problem. So it say that here it's just it says come up with some algorithm to solve certain kind of question. But we say some problem is a decision problem if what algorithm has to do is just to return yes or no. Okay. So the key part of the decision problem is it's just return yes or no. So input can be quite complex, but in the decision problem case, the output can be, I mean, output is extremely simple. It's either yes or no. And in fact, the propositional logic that we covered kind of generate a few decision problems. I just listed 4 decision problems. The first decision problem is satisfiability. Here, the input is formula F. The output should be an answer to whether this formula F is satisfiable or not. Validity, the input is again the formula. The output is whether the formula is valid or not. Entailment, in this case, input is the 2 formulas. Inputs are 2 formulas. And then the output is whether the first formula F entails the second formula G. The last one, equivalence, is input. Again, the inputs are 2 formulas. The output is the equivalence. We're checking whether these 2 formulas are equivalent or not. All of these are decision problem because in all of these cases, what we have to do is to return yes or no. But it turns out if we have a solver for one of them, we can generate a solver for the other. Okay. So here's an exercise. I mean, we did something like this before, but here's an exercise I want you to do in a bit different angle. So suppose we have a solver for equivalence. So we have a solver for the last case. So this guy. And then, so we have a solver for the last case. And then this question asks you to implement solver for the other 3. So satisfiability, validity, and entailment. So that's the first question I wanted to think about. The second question is, I mean, the equivalence question is, I'm asking whether this equivalence question belongs to NP. So I will tell you a bit more about what this NP means. So perhaps you heard about the in the complexity class NP or co-NP, I mean, polynomial time, I mean, NP, or maybe some of you even know about co-NP and the polynomial hierarchy and so on. But so these are the characterizations of an algorithm in terms of their time complexity. But their time complexity uses some different type of computation model. So polynomial time just means that you have an algorithm, then when you run an algorithm, it runs in polynomial time. But the co-NP means it doesn't mean it's a not polynomial. It means a polynomial in non-deterministic Turing machine. In deterministic Turing machine. Okay. What does this mean is intuitively is that when we solve some problem, we might imagine doing some non-deterministic choice. So sometimes your algorithm might want to go set some Boolean variable to 1, or sometimes you want to set Boolean variable to 0. And typically, when you implement such an algorithm in Python or maybe some other programming language, you have to make a decision. But in that machines like a non-deterministic Turing machine, you don't have to make a decision. You just leave the machine to explore both branch. So the algorithm initially have some maybe just running with one maybe process, but then at some point mean, conceptually, the algorithm may fork and may generate the two processes. If each of them explore different decisions about the computation, and so on. So, and then that if it may, but then if this algorithm should belong to NP, all of these forked processes should end in the polynomial time. Okay. But the computation depth should be a polynomial time in the size of the input. Okay. So now, because suppose this algorithm is solving decision problem, so then maybe we might get some very confusing answer. Maybe this guy that may return true. Maybe this guy may return false. So maybe this guy may return false. Maybe this guy return true. Now, for NP, this final post-processing is fixed. Okay, so we can't really change it. The final post-processing, and after that, we can't really do anything either. So final post-processing is fixed. The post-processing, what it does is that it just look at all these possible outcomes, and then for the possible outcomes, if there exists true appears at least once. So in this case, true appears here at least twice. In that case, the final output is true. But if truth doesn't really appear anywhere, so if this one was false, and this one was false, so truth doesn't appear anywhere, then in that case, this algorithm, the file post-processing will return false. Okay? So that's how this non-deterministic Turing machine, this non-deterministic Turing machine works. We run, it can fork as many at the different kind of decision points, and so you can go like this. But if something should belong to, some algorithm belong to NP, that's every branch should terminate in polynomial time. And then final post-processing is fixed, but final step of gathering all the results is fixed. And that step check whether if there exists only true appears only once on the final output step, not only once, at least once, it returns true. If true doesn't appear anywhere, it returns false. So that's what the NP algorithm does. And then there is something called co-NP. Co-NP is very similar to this NP setting, but it assumes a different kind of post-processing. Okay, in this co-NP case, if true appears everywhere, so then we return true. But if false appeared at some point, like this, then it returned false. So NP and co-NP, they are assuming very similar kind of computation model, except that the last steps, they are different. That's kind of answer collecting step is different. NP case, if one of them returns true, the answer is true, otherwise false. Co-NP case, if all of them returns true, the answer is true, otherwise false. Okay. Now, interesting question is, if you can show NP is equal to co-NP, I think you can retire and become a very famous complexity theorist. So there are many open questions in complexity theorist. So co-NP is equal to NP, which means if some problem has a NP algorithm, is it going to have a co-NP algorithm always, and vice versa? If you can solve this equality, then I think you will perhaps get a big prize and can retire. But this is a very hard open problem in complexity theory. But anyhow, so that's a kind of short introduction about NP and co-NP. Now I will give you maybe 3 minutes to think about the exercise 1 and exercise 2. Okay, let me answer these questions. Sure. So here's a way to encode all the questions. So for satisfiability, say, if you want to check satisfiability of F, then what you need to do is we just check equivalence between F and false. Okay. And then if checking the equivalence between with the F is equivalent to false, that means it's not satisfiable. If F is not equivalent to false, that means it's satisfiable. So we just put we negate each answer and then return it. So that's our algorithm for set. And then you can do something quite similar for validity. So in this case, you can just check equivalence between the given formula F and true. Interesting case is an entailment. So if I want to check F entails G, okay, that means F implies G. Then here's how you can do it. You check equivalence between F and G. Okay. And as you will see, or maybe you may or may not be quite familiar, but we can actually show by using semantics if F is equivalent to F and G precisely when F entails G. Okay. I mean, this means F and G is typically stronger than F. It implies F, but they can be the same only when, I mean, that G doesn't really add any new informations into F. Okay. So that's this F, only F implies G. So only then this implication is true. Right. So using this effect, we can use this encode this entailment. For the second question, it's not NP. I mean, that's because here's only intuitive reasons for why it's not NP. Intuitively, NP is a bit like a satisfiability problem. So I showed you maybe. It's all mixed up. So let me just erase this first. Okay. So I said the NP is really return or true if one path find the true value. And then co-NP case, it returns true when all the paths find the true value. Now, imagine that this branch only happens when we want to decide whether a certain propositional variable has a value true or false. So this branch really explores either true case or false case. So branch like this is really boils down to setting some propositional variable 1 and setting propositional variable 0. So then the existence of one path which returns true, like this, that means, I mean, this corresponds to a assignment that makes some formula to be true. And then the second case, in the co-NP case, all the paths should be true. That corresponds to all the assignment that has to be true. Okay. So although I'm not going to show it kind of formally, or the questions that involved whose specification involved exist, like satisfiability, it corresponds to the NP problem. And in fact, it's a so-called NP complete problem, the most difficult problem in the NP class. And then the question that involves universal quantification, like a validity, it has to be true for all the assignment or entailment. It has to be true for some I mean, the relationship has to be true for all the assignment and so on. So validity, entailment, equivalence, all of them correspond to the so-called belong to this co-MP class. So they are co-MP problems. That's because they are problem is specified by, the specification of the problem really involves looking at all the possible assignments to the propositional variable and want to make sure they are all satisfy certain specification. Okay, let's go to the next. So then this lecture, we're gonna focus on the equivalence. And then just like the satisfiability that I told you, you can check equivalence by brute force, and which is just use a truth table, but this will always take exponential time. So a bit better approach is to have using some rules. So then using rules, sometimes we can prove equivalence to two formulas in much more efficiently. And then so this is called equational reasoning, and there are some solvers based on the equational reasoning. And then the idea of such a solver is to follow these two steps. Two design steps of the solver. The first step is to come up with a basic equivalence, the set of basic equivalences. And then the second step is to allow these basic equivalences to be applied to any subformulas in any given formula. Okay. So just to say, to rephrase what I just said, we can check equivalence by brute force, just using the truth table. That's highly inefficient. A bit better approach is to use some rules to do the proof. And then these rules can be constructed in the two-step process. The first is you think about basic equivalence, which we can apply. And then the step two is that we allow these equivalences to be applied to any subformula. Okay. So then this brings the next question we have to think about is, what are the appropriate basic equivalences? And here comes the idea of a Boolean algebra, which is invented by this George Boole that you see on this slide. So this Boolean algebra is a collection of multiple rules. Okay. So, and then, if you look at all these rules, it looks just too complicated, and then you might not be able to see any structure there. But actually, these rules have some nice structure. The first structure you can see is that all the rules come in pairs. So the usual one and then its dual version, both of them belong to the Boolean algebra rule. So for instance, if we take the rule here, so you say that it's a distributivity, it's that the conjunction distribute over disjunction. But if I switch AND by OR, this OR by AND in everywhere in this equivalence, then you get another rules in the Boolean algebra. And that's always the case. If you look at observation rules, if I have an AND and OR, if I switch them, then that again give another rules. And in the top case, the identity rule, we switch AND or and false, true by false, and then we again get a rules. So in some sense, what all these rules say is that we have an AND and OR, true and false, and the rules are satisfied with a self-dual. So that's what this first property says. And then the other axioms are, if you are already familiar with some algebraic structure, and they are all related to very well-known algebraic structure. Sorry. So these first three rules, they correspond to so-called commutative monoids. Okay. So I don't know how many of you heard about monoid or not. So but you may heard about something called the groups. Maybe not. So monoid is a set with a binary operation and unit. And then this binary operations it works like a plus operations for natural numbers. It satisfies associativity and the commutative. Especially commutative monoid is satisfied commutativity, and then the constant serve as a unit. So right. So in this case, these three rules say we have a two commutative. So if you replace this equivalence by equality, regard this equivalence by equality, then these three rules say we have a two commutative monoid over the set of propositional logic formula. The first monoid is it's a formula, and then the constant of the monoid is true, and then the other binary operation is AND. Okay. So this commutative monoid axioms say this true should be the unit of the conjunction operation. So it satisfies these identity rules. And then because it's commutative, this conjunction has to be commutative. And the last one, associativity, is the remaining axiom of the commutative monoid. And then the other three rules say actually this formula have another commutative monoid, which is false and disjunction. So these three rules say we have two commutative monoids, and it doesn't tell us about the interaction between the two. And then that interaction is described by the next formula. That is, I mean, if you satisfy all these four, that's called bounded lattice. And although it's a bit hard to remember, this one really kind of right. Both these rules say by using conjunction and disjunction, we can define the implication. I mean, we can define when one formula entails the other. So we saw before that we can use f and g is equal to equivalent to f, and we said that's equivalent to say f entails g. And similar way we said f or g. And that is again equivalent to f entails g. So there are two ways of defining entailments. And then these observation rules say that these two ways are consistent. So I mean, you can see there are two different ways of defining entailment in some sense. These observation rules, you can read it as the rules, but one consequence of this is that they allow us to define entailment by just equationally, and then these two different ways of defining entailments are essentially the same thing. So that's what this rule is saying. And the last rule is the next rule is called distributivity. It says the conjunction distributes over disjunction, disjunction distributes over conjunction. So in this sense, this conjunction, I mean, some people, it's a bit like a multiplications for numbers. Disjunction is like addition in the numbers. So typically this multiplication distribute over the plus, but not the other. This plus doesn't distribute over multiplication for the numbers. But for this Boolean algebra, I mean, this distributivity is completely symmetrical. So conjunction distribute over disjunction, disjunction distributes over conjunction. The last bit is talking about giving the meaning of the negations. And it say that if you take a f and its negated version, it's equal to false. F and its disjunction of its negated version, it becomes true. Okay. So this is the rules for the Boolean algebra, and it turns out this is, this is complete. If we are allowed to apply these rules for any subformulas and replace the subformula by something else, and then this completely characterized logical equivalence. So that is some hard result. I mean, these rules are, you can say it's all obvious by looking at the semantics. You can easily derive it, and you're already familiar with this. But difficult part is that these rules are good enough. We can use them to show all the other rules. So here's an exercise I want you to do. Okay, erase this. Okay, using the rules in the previous slide to show, these rows. So I will give in the remaining maybe 6 minutes, I want to solve this question. Then I think to solve this, maybe it's better to look at all those rules. So let me open another window. So if you have a PDF file, you can look at PDF file and then try to use those rules to show this. Otherwise, I will soon show you the previous slides here. Okay, so the rules that you see on the second slides, and what I want to do is use the rules here in the then prove the rules that you see on the other slide. So if you finish, then you can leave. I mean, we have about 5 minutes left, and then. But while solving these problems, if you have any questions, you can ask me those questions. Yeah, maybe I'll show you one case, because so if you are not familiar with this, you feel that it's super difficult. Okay. So let's try to show this one. So f and f is equivalent to f. So here's how you can do it. So you start with f, and then, well, okay, right. So we start with f and f. Now we know that this is equivalent to f and f or false. That's because of this rule for identity law that you see on the right-hand side. So then now, because now if you have this f or false, then we can use these assertions that if you have a conjunction, then some terms which involve disjunction, that's identical to f. So we can say this is the same as f. But that's how you can derive this equivalence. So the rule is a bit similar, but it requires a little bit of creativity to come up with something like the term that you see here. Yeah, so we're gonna see the solutions of these, some of the solutions of some of these rules in the beginning of the next, on Monday, no, Wednesday. So that's it for today. I'm gonna hang around here for about 5 minutes. So if you have any questions, you can just ask me. Okay, so that's it for today, and thank you all for attending.